So we turn our attention today away from kind of the nuts and bolts of the chemical reaction equation and into the actual chemical reactions themselves. And so a lot of what we're going to be talking about today are the things that are related to the reaction and its progress. In particular, we're going to be looking at things like reaction rates, how fast a chemical reaction goes, some of the factors that get into that, and then probably the most dangerous and well-known hazardous reaction, the combustion reaction. So again, that's where we're going to spend the majority of our time today. And then our next class, we're going to talk more about types of fires and fire extinguishers, and that'll round out the chapter for us. So when we talk about rates of reaction for chemistry, what we're talking about is the speed of the reaction. How fast do we get to the products from the reactants? And while we tend to think of chemistry as being this process of really fast chemical reactions, you light something on fire, it burns, it goes fast. A lot of chemistry is actually spent in slow reactions, reactions that take a considerable amount of time. And that's mainly because most of the chemistry that occurs is not hazardous. A lot of what we associate with hazard has to do with speed. The faster it goes, the more we have to pay attention to it because it could start to go out of control, and we need to figure out ways to control it. So when it comes to rate of reaction, there are 7 factors that we're going to look at that impact the reaction and its speed. So we're going to go through each of those 7 here in turn. The first is the nature of the material itself. Now, our focus here again is mostly on combustion reactions because combustion reactions tend to be the ones that are the most violent and the most hazardous, the ones that we kind of associate with fires, explosions, and other kinds of things. So the first thing that we would consider is, well, is this substance flammable at all? Because some substances don't burn. Water is a great example of it. Doesn't matter how hot we get water, it's not going to ignite. Some substances, they'll burn when we give them an ignition source. So right now, I'm holding up a piece of paper. This piece of paper is flammable, but not in its present state. I can hold this paper up forever. It's never going to burn. But if I introduce an ignition source to it, if I bring a lighter up to it, then yes, it'll ignite, it'll burn. It has that potential. But you have to bring that potential to it. And then there are some substances, phosphorus, for example, white phosphorus, that burns completely on its own. You just have to introduce it to air. So there are varying degrees of ignitability. And how ignitable it is just based on what it is going to impact how we treat it and what kind of hazards we associate with it. Most of us aren't going to consider paper to be a hazardous material. But in the proper context, if it is part of something else, then yeah, it's got its rightful place. A second factor, subdivision of reactants. So what do the reactants look like? How much surface area is exposed? most of you guys are in here are welders. What do you have to worry about when it comes to metals? Working on a metal surface, maybe grinding on a particular metal. You got to worry about dust explosion. You got to worry about the shavings igniting, especially if you're working with something like aluminum. So when you're grinding and you're creating these small particle-sized metal pieces, they're much more prone to fire than a giant sheet of aluminum. That's the nature of subdivision. The more surface area that is exposed, the more dangerous it is. Dust explosions are a real thing, especially certain types of metals. Get them into a fine powder or a dust, and if the conditions are right, you can have an explosion on your hands. So the thing that we have to think about with this is, again, surface area. The smaller the particles are, the more collective surface area that they have. And I know that's kind of weird to think about because, you know, if I gave you the question, which has more surface area, metal shavings or a sheet of aluminum, you'd probably say the sheet of aluminum because you're thinking, well, the sheet of aluminum is definitely bigger. That's not a fair comparison. What we really need to compare is, let's say that I have 10 grams of aluminum. One 10-gram sample is a sheet of aluminum. One 10-gram sample is aluminum shavings. If we're talking about the same amount, then the finer particles are going to have way more surface area because there's not as much unexposed aluminum. So the smaller those particles get, the more total surface area they're going to have. And the more surface area that they have, more easily they'll ignite, the faster they'll ignite, and the more likely they will be to cause a chain reaction combustion. The thing of it, kind of the same way you think of a magnesium flintstone. If you've ever seen anyone try to light a fire with just flint rock, they can stand there and they can bang those rocks together forever. May not get a whole lot of a spark. But if they shave some of the magnesium off first and then start to strike, the spark that they create can ignite the magnesium, which can ignite the rest of the kindling. It's the same thing. If you don't shave off that magnesium, if you just leave it as a big piece, it doesn't do it. Maybe you're fans of the TV show Survivor, which has been on for now forever. That's one of the challenges that they often have to do, especially when they get into tie-breaking situations. And if you watch them closely, that's exactly what they do. They have to shave off magnesium, then they have to strike the stones to get the sparks to get the fire to start. It's a lot of practice. But the chemistry behind it is exactly this. Another factor, state of aggregation. The physical phase of the thing that you are trying to react matters a lot. It has a lot to do with mobility. The more mobile the substance is, the more easily it can mix with other substances, the faster it reacts. So gases are the most dangerous phase when it comes to reactivity. Liquids are second, solids are last. And again, it comes very similar to the idea of surface area. Gases especially can spread out, diffuse in many directions. So when it comes to igniting, when it comes to getting a mix that can ignite, you're going to see it happen a lot faster in the gas phase. In fact, when we talk about flammable substances, one of the things that is tied to their flammability is how quickly they can get vaporized. The more quickly a flammable substance vaporizes, the more dangerous it is. Faster it'll actually react. We also can look at things like concentration. Now, concentration usually doesn't make a whole lot of difference in combustion reactions because very rarely do we talk about solutions that burn, but it does make a difference when we're talking about other kinds of chemical reactions. And the idea of concentration is just how much stuff, how much reactant is packed into a given amount of volume. So the more concentrated it is, more of that reactive material we have present, the faster it goes. And so what this is getting into is the idea, in order for a chemical reaction to take place, the molecules of the substance actually have to collide. They have to knock into each other. Now, simply knocking into each other isn't enough to produce a chemical reaction. You have to have a couple of other factors. You have to have factors of energy. You have to have factors of molecular orientation. Lots of things go into it. But if I have more particles present, the odds, the probability of some of those reactions occurring increases. Think of it like the lottery. You play the Powerball. I heard an ad this morning. Odds of you winning the Powerball are somewhere north of 1 in 290 million. So on any given day, your odds of winning the Powerball are pretty low. But as the jackpot grows and more people play, the odds of somebody having the correct combination of numbers increase. Your odds don't increase, but the collective odds of everybody who plays do. Because the more tickets that are bought, the more combinations of numbers that are played, the more likely that the correct combination ends up getting chosen. And so that's always been the fallacy of lottery is, oh, well, when the jackpot gets really, really big, our chances of winning go up. No, your chances of winning are always the same. The chances of somebody winning increase. And so what sweeps the nation is the concept of, well, why not me? My odds are just as good as anybody's, why not me? Activation energy. Talk about this. We can go back to the example of paper. The reason this paper will not ignite on its own is that it doesn't have the proper activation energy just from the root. Activation energy is an energy minimum that is necessary for a reaction to occur. Now, for some substances, energy is the energy of a room, the energy of room temperature is more than sufficient for that. And that's why materials like white phosphorus are self-igniting. But the reason this paper won't ignite unless I introduce some flame to it is because the flame provides the activation energy to start the combustion reaction. Once the combustion reaction begins, the energy released by the combustion reaction becomes enough to continue the reaction. So activation energy is usually fought using heat sources. You raise the temperature of something. There are other means of doing this: shock, detonation, electrical impulses. There are other ways of getting to this activation energy, but heat is the most common of these. Closely related to that is the factor of temperature. Temperature kind of fits into a number of these, because if we increase the temperature, we're also raising the amount of energy coming into the molecule. That could be enough to help it overcome the activation energy. By increasing the temperature, we're also increasing the molecular motion of the molecules in the sample, so the chances of them colliding are more frequent. Generally speaking, a reaction rate can double every 10 degrees Celsius temperature increase. So in Fahrenheit, that's 18 degrees. So every 18 degrees, you can see a doubling in the reaction rate. So this reaction occurs at 72 degrees. It'll occur twice as fast at 90 degrees. It'll go 4 times as fast at 108 degrees. And so on and so on. It doubles every 18 degrees or so. And it all has to do with molecular motion, increasing the movement of the particles, increasing the number of collisions, and helping to raise that energy threshold to try to get us over that activation rate. And then finally, there's catalysis. Catalysts are substances that we can add to a chemical reaction to help the reaction go faster. But there's 2 important things about catalysts. First of all, the catalyst itself is never used up in the course of the reaction. And secondly, it usually works by lowering that activation energy. Now, there are multiple types of catalysts. Most common catalyst that you are probably familiar with is in your car. In the exhaust system of your car, you have a catalytic converter. The catalytic converter contains usually palladium or sometimes platinum. And the whole purpose of it is to provide a surface on which the noxious exhaust fumes literally stick onto to help them find extra oxygen in the air to turn them into less dangerous materials. So one of the common incomplete combustion byproducts is carbon monoxide. So especially if you are idling or you're in a confined space like a tunnel or a garage or something like that, the fuel that you burn doesn't get burned up completely. Instead of converting completely to carbon dioxide, it converts to carbon monoxide. Now that can be especially dangerous, but if you are in an open air atmosphere, the catalytic converter will take that carbon monoxide, will basically stick to it, and as oxygen comes in, it'll also stick to the converter, and it'll allow that carbon monoxide to turn into carbon dioxide, which isn't nearly as dangerous. Similar kind of things can happen if you have nitrogen-based compounds coming out of your exhaust. We can turn nitrogen monoxide into dioxide as well. But that's what the catalyst does. So that's what the surface catalyst. The surface catalyst basically just gives a place for the thing to stick on. There are other catalysts that actually participate in the chemical reaction, and those catalysts, what will happen is they will react in some kind of way and then redeposit at the end of the reaction too. So in the end, the catalyst always comes back to us. It's always there. It does not get used up in the process. Now, some catalysts do get dirtied up in the process of their reactivity, and they need cleaned up from time to time. That's really all that they need. So those are our 7 factors that increase the rate of reaction. We're going to move now into talking about combustion reactions and understand that we know what a combustion reaction looks like from the chemical standpoint. We've got something reacting with oxygen, and we get a series of oxides as the product. But what we also will see in combustion reactions are the release of energy, and that can come in the form of heat and or light. Now, the heat is almost always there. If something is burning, we feel it. The light isn't always necessarily present. A lot of it depends on what is burning and what kind of the nature of those characteristics are. So, low molecule alcohols like methanol, ethanol, when those burn, a lot of times they burn without an actual flame. You feel the heat on them, but the flames, if you can see them, are in the kind of light blue range. So you feel the heat off them, you don't necessarily see them. And so part of that is just based on there are certain frequencies of light that we cannot detect. And if the lighting characteristic, if the energy characteristic is the right way, it's just in the region of the light spectrum that we can't see. That's why we don't see the flame. But we certainly can feel the effects. Combustion reactions are oxidation reduction processes. Talked about that last lecture. We saw the oxygen inserting itself into the other molecule. So if there was a hydrocarbon, we saw the oxygen reacting with the carbon to make carbon dioxide, and with the water, or with the hydrogen to make water. When we see combustion reactions with other substances, they occur in kind of the same way. Sulfur compounds burn in oxygen to make sulfur dioxide. Sulfur dioxide is a chemical that has a very powerful odor. You can associate it with burning hair, burning tires, kind of that strong, pungent, knock you on your backside kind of odor. But combustion reactions are also self-sustaining. So they might require some energy to kickstart them. But once we kickstart them, using a flame, using some kind of ignition source, electrical shock, whatever it is, their reaction produces enough energy to keep them going so long as there are certain things present. You have to have enough fuel, you have to have enough oxygen. Once we have all those things, the reaction keeps going and going and going. Now, when it comes to these kinds of reactions, you have to understand we are always going to have some sort of fuel. That fuel is going to be in the gas phase. So even if it is something solid that is burning, you have to understand that that substance is vaporizing as it burns. So kind of the best way to prove that to yourself is if you think about anything that burns. It always burns on its surface. Never burns interior. You make a fire in your fireplace, the interior of the logs is never burning. It's always the exterior. Part of the reason for that is access to oxygen. The other reason for that is because as the heat of the reaction is coming into those logs, the compounds on the surface of the logs are vaporizing. They're going from the solid phase to the gas phase. And it's the gas phase stuff that is interacting with the oxygen to continue the combustion reaction. So it doesn't matter what our fuel is, solid, liquid, or gas. If it doesn't vaporize, it's not going to burn. It has to be in the gas phase. It has to be able to be turned into the gas phase in order to burn. The combustion process will always give us oxides because oxygen will always be the thing that is burning the substance. So if we have a metal fire, we're going to get metallic oxides. If we have a non-metallic substance, like wood, like sugar, like paper, like most fuels, then they're going to be non-metallic oxides. And again, the oxygen just inserts itself into the other elements in that substance. As we have seen, many combustible substances have carbon in it. Carbon dioxide is one of the most common byproducts of combustion. Water is not close, not far behind. There's a lot of substances also contain hydrogen. Now, in the process of combustion, there are two different kinds. There is the complete combustion. This is the combustion process where all of the carbon is turned into carbon dioxide. We see this kind of process occur when we have abundant oxygen available. So excess oxygen is going to be a key component to complete combustion. If we do not have plentiful access to oxygen, we will not get complete combustion. What we will get instead is incomplete combustion. When we are short on oxygen, again, most common example you can think of, if you are idling, the car sitting in one spot and not moving, you're burning tons of fuel, but you're starting to kind of run out of oxygen around the immediate area. What happens as you start to run low on oxygen? The combustion process takes shortcuts and gives you carbon monoxide, carbon dioxide, or even just plain old carbon in the form of soot. If there is plenty of oxygen available, then that's, that's what you will get instead. Most all of it will turn into carbon dioxide. And if there is little bits of carbon monoxide that sneak through, catalytic converters actually turn into carbon dioxide before they get pumped out of the exhaust pipe. All right, last thing that we'll talk about today is in the chemical energy. So we've talked about this a little bit. Chemical energy is ultimately what gives us that energy release. So we know that to break the bonds of the hydrocarbon fuel, we're going to have to input energy to get the fuel molecules to break apart. That's what the activation energy is for. But once those dissociated atoms start to bond with oxygen to create those oxides, the formation of those new bonds releases tons of energy. And those tons of energy are what come off to us as the heat and the light we associate with combustion. Now, how much heat and light really varies based upon what it is that we have. Some materials are put together a little bit differently. They're going to give us more energy because it's not going to take nearly as much energy to break them apart. Others are going to require more energy to break them apart. And so as a result, they're not going to give us quite as much energy on the backside when we're done burning them. It's a case-by-case kind of basis. And so that's where we will stop for today. Again, on Friday, we will get into more about the combustion reaction. We'll talk about types of fires, fire extinguishers, hopefully finish out the unit. So thanks for coming today. Have a good morning. See you later.